Hey there, and welcome. If you're ready to turn those super tricky laws of motion problems into your highest scoring questions, then you have absolutely come to the right place. So let's dive right into this blueprint for mastering dynamics.
You know, we've all been there. You see one of those problems with all the blocks and pulleys and inclines, and your brain just kind of hits a wall. But what if I told you there's a system, a step-by-step approach that can solve pretty much any of these? Well, we're going to build that system together, starting right now.
Everything we're about to talk about, every single complex calculation, it all hinges on one single foundational rule. I'm telling you, get this one thing right, and you are already halfway to the correct answer.
And that step? It's drawing the free body diagram, or FBD. Seriously, this isn't just a suggestion, it's the bedrock of your entire problem-solving method. So let's make sure we know exactly what it is. The real beauty of the FBD is its simplicity. It's not supposed to be some detailed work of art. Its power is in its clarity. You take one object out of the whole system, just the block, or maybe just the pulley, and you just draw it as a simple dot or a box. Then, you draw arrows for every single external force acting on that one object. It's this act of isolating it that prevents so many common mistakes. So here's the deal. You've got to follow these 3 steps every single time, no exceptions. 1. Isolate the body. 2. Draw all the forces. I mean everything. Gravity, normal force, tension, friction, any applied forces. Don't you dare miss one. And 3. Set your coordinate axes. And hey, here's a pro tip. If you can, always try to align one of your axes with the direction of acceleration. It's going to save you a ton of math later on. Okay, so your FBD is drawn. You're feeling good, right? But hold on. Before you jump into F equals MA, there's a quick mental checklist. And honestly, this little checklist is what separates the top scores from everyone else.
This equation, Newton's second law, this is our destination. The whole reason we draw the FBD and do all this analysis is to correctly figure out what to plug into this powerhouse of an equation. But to get there, we have to ask one really critical question first.
This is such a classic exam trap. You get a problem with friction and you just immediately start trying to calculate the acceleration. But what if the force you're pushing with isn't even strong enough to overcome static friction? You have to check first.
So here's the check. It's super simple. You just compare the force you're applying to the maximum possible static friction. If your applied force is bigger, great, the object moves, and you'll use kinetic friction. But if it's not, then the net force is 0, and the acceleration is 0. That's it. It's a tiny check that can save you from a huge mistake. The second thing you want to check is how all the parts of the system are connected. We call these constraint relations. Basically, if you have blocks connected by a string, they're constrained. As long as that string is tight and doesn't stretch, if one block moves down by a centimeter, the other one has to move up by a centimeter. This means their speeds and the size of their accelerations have to be exactly the same. Spotting these relationships is key to setting up equations you can actually solve. All right, now for the part that can feel a little bit like a magic trick. We're going to look at those really tough trick questions. You know, the ones set in something that's already accelerating, and I'm going to show you the secret to making them surprisingly simple. You've probably seen this one before, right? It feels so complicated because you've got the block moving on the incline, but the incline itself is moving inside a truck that's accelerating. It's just a headache, unless you know the secret of pseudo-force. So what is this secret weapon? A pseudo-force isn't a real force, like gravity or tension. Think of it more like a mathematical tool. It's a fake force that you add to your FBD, and it lets you pretend that an accelerating system is actually standing still. And here is the aha moment. By adding the pseudo-force, which is just the mass times the frame's acceleration, but pointed in the opposite direction, you're basically changing your point of view. You get to solve the problem as if you were sitting right there inside the accelerating truck. And from your perspective, it just becomes a simple statics problem. You've cleverly shifted your reference frame to turn a really hard problem into a much, much easier one. That's not magic, my friend. That's just smart physics. Okay, so we've covered the core techniques. Now let's switch gears and talk strategy. On any exam, some topics just carry more weight than others. To really max out your score, you've got to know where to focus your precious practice time. Think of this list right here as your treasure map to the big points. Now, why these topics? Well, it's because examiners love them. They're perfect for testing multiple concepts all at once. A single question about an inclined plane can bring in FBDs, friction, and Newton's laws all together. If you master these zones, you're learning how to pull all the core ideas together, and that's what earns you those top marks. Let's just take a quick peek at one of these, apparent weight in a lift.
We've all felt this, haven't we? An elevator starts going up, and for a second you feel pressed into the floor. Or it starts going down, and you get that little fluttery feeling of lightness in your stomach. Well, that feeling, that's your apparent weight, and physics explains it perfectly. This table breaks it all down. See, when the lift accelerates up, the floor doesn't just have to support your weight, it also has to push you upwards to accelerate you. So that normal force is bigger than your weight, mg. You feel heavier. When it accelerates down, gravity's already helping, so the floor doesn't have to push as hard. The normal force is less, and you feel lighter. And of course, in free fall, you feel totally weightless.
So the key thing to remember is this. Your actual weight, your mass times gravity, that never changes. What you feel as your weight is actually the normal force from the floor pushing up on you. That's the thing that changes. And that is the true definition of apparent weight.
Phew, we have covered a lot of ground, right? From the most basic rule to advanced tricks and even exam strategy. So let's boil all of this down into one final actionable plan.
This is it. This is your 4-step blueprint for success. Number 1, always, and I mean always, start with a clean free body diagram. Number 2, do your pre-calculation checks for friction and constraints. Don't skip it. 3, use that pseudo-force trick for any of those non-inertial frame questions. And 4, use that treasure map we talked about to focus your practice on the topics that give you the biggest bang for your buck.
Look, this isn't about just memorizing a bunch of solutions. It's about mastering a method. Really internalize this process, apply it over and over again to past exam questions, and I promise you, you will build the skill and the confidence to walk into that exam hall and just knock these problems out of the park.
So, I'll leave you with this question. Look back at that treasure map. Whether it's the connected blocks, friction problems, or circular motion, pick one area. Decide that you are going to absolutely own it. So, where are you going to start?